So this is the first chapter entitled Random Walks, Brownian Motion, and Stochastic Models of Security Prices. Okay, so here we present the idea of representing asset prices using a random variable approach. In fact, a deterministic system is a system where we don't use any probabilistic approach to the model. That is, if we know, let's say, we are here, we know the information, let's say, on the capital, so the investment in a certain asset. So I am for sure, let's say this is 1 year ahead, I am for sure aware of what will be the interest here. So when I'm speaking of interest, will be either profit or gain or loss with regards to the investment here. Okay, so let me give an example. So let's say you invest M here in the bank, and I'm saying to you that we have R% per annum. That is, you get an interest of R% per year when you invest 1 rupee. So here, let's say you're investing M rupees, and here it is 1 year. So what will happen? It will be M exponential or times 1 year. Okay, so this is the continuously compounding interest rate. Otherwise, it will be this. I think you know this. So the interest rate model, which is deterministic, is given by this. So this is equivalent to this. How do we know? So for example, let's say we want to integrate both sides here. So first of all, let's put all M on the same side. Okay, let us integrate both sides. So let's say I want to integrate from 0 to t, 0 to t. Okay, so what happens on the left hand side? I will get ln of m equals to, or is deterministic, so we can put it outside. So it will be t here. So this means that I will get ln of mt minus ln of m naught equals to rt. So I will get mt over m naught equals to exponential rt, which means that my investment of the t years, will be mt equals to m naught exponential rt. So my capital is, my investment is m naught, or is the interest rate per annum, and t is the number of years. So the number of years, not necessarily a whole number. It may be 0.5 years relating to 6 months, for example. Maybe 1.5 relating to 18 months, etc. So R times t, the number of years, exponential of that RT times the initial capital. So you get your investment here. So it is a generalization. So here it is m naught. So it is t years now. And what is mt? It is something which is known for sure. So I can do this calculation when I'm still here. So this is the present and this is the future. Okay, so this is a deterministic approach. Now, in classical mathematics, applied mathematics, we usually employ deterministic systems. However, the factors affecting the movement of stock prices on the market are so numerous and complex that a deterministic system won't suffice. It won't be adequate for the different fluctuations that happen on the market. That's why we need to adopt a stochastic approach. And this is what we will see in this section of this module. Okay, so a stochastic system contains a random input in its evolution and hence has an uncertain future. We will see the model in the next slide. So as an illustration, suppose at time t, an asset has a price x. Okay, at time t, good. The asset has a price x, so let's put it xt. At the next instant, so I put it here, t plus dt, where dt is the increment in time. Normally, dt is very small. It's a small time increment, time change. Okay, so what happens to xt now? Xt becomes xt plus txt now. Can remove the t here in the dx. So it is xt will be the price here. The price of the asset will be xt, the previous price, plus an increment, a change if you want. So it may be negative or positive. Okay. So what we assume here, we assume that there are two influences on this change dx. First, perhaps there is a drift. Okay. So predictable. So the part which is deterministic, if you want, we say that there is a risk-free contribution in time dt. So here we assume that mu is the risk-free contribution. Okay, so it is a drift. So perhaps say if I put it here, so this is xt, so we are at t here, and let's say this is dt. So perhaps when you analyze the previous time instance, you see that the price of x, let's say it is gold, it is having an upward trend. Perhaps in the next instant we will expect it to be also increasing. So if we are speaking strictly of the trend, it should be like this. Okay. So this is the general movement pattern of trend of my asset. So that mu will be positive here. Okay. Now it may also have a zero trend also, maybe like this, or it may, for example, be negative trend. So your mu will be negative here. Okay. Now on the market, when you analyze the evolution of price, you won't see, for example, that the price go up like this. This is not true. You will see that it will go perhaps over the long run. You will see an upward trend, but the evolution is quite clumsy, has variations around that general trend. So that variation will be rated as the unpredictable, the stochastic one. So it is the stochastic contribution in time dt. And we write it like this. It is sigma dbt. Okay, so dbt is a number that we will see. It is a random number that we will see in the next slide. What is that dbt? Okay, so this is a technically known as Brownian motion. So we will see that later on. We will see the properties of the Brown motion later on. Okay, and sigma is known as the volatility of the asset. So the higher the volatility, the more spread. For example, let's say for the black one, sigma is, let's say, is sigma star. And let's say that the new trend relates to 2 sigma star, let's say. So you will see that the variation around that general trend will be wider. Okay, and then our model is given by this dx, which is the change in my asset price, given by the deterministic part, which is known as the drift, and the random part, which is known as the random volatility. Good. So this model that we have seen, in fact, we understand that it is given by a stochastic part here. Okay, and this plays a very important part in this equation. So it is known as SD, stochastic differential equation. Okay, so it is a particular type of stochastic evolution known as the Brownian motion. So we will see that Brownian motion later on. Okay, so I would like to highlight that is actually an example. So later on we will see uh, a particular SD, stochastic differential equation, that we will be using for stock pricing, stock modeling, okay, stock price modeling, okay, which will be later on be used for the pricing of options. Good. So this is just an example, an illustration, but this part is quite, we will say, quite similar in every model. Okay. So it has this feature of a drift and the feature of the sigma part. But in some cases, your mu may be, in some cases, your mu may be a function of x itself and of time. So your mu won't be a constant, it will be comprising x and t. And this also, this sigma, for some model, we may see that it may be a function of x and t. Okay, so these are more complex models. So especially for interest rate models, for example, your mu will definitely comprise the x here. So we will discuss other types of stochastic models for price evolution later. Okay, before discussing the continuous version of asset price dynamics, we will consider a discrete model. So what we just presented to you is a continuous model. If you want continuous time model, so it is defined on the time axis, so on the continuum of the time axis. Okay, so to better understand what is happening, we'll try to consider a discrete model. So what is a discrete model? So we'll take specific time instants on the timeline and then try to see how do we build until having the Brownian motion. So here we define the random walk, which will later on. So random walk is defined on the discrete time model, the discrete time axis. So we will see that later on. We will link this to the Brownian motion that we want to define here. So we use the notation n mu sigma squared to denote a normal distribution of random numbers with mean mu and variance sigma squared. So this is quite familiar to you. So consider the random walk BNT. Okay, so your BNT here is denoting the discrete time process, which is the random walk. Okay, so we define it like this. Bn0 is equal to 0, so it is starting at 0. So at time 0, when t is equal to 0, Bn0 is equal to 0. The spacing between the time steps is 1 over n. So your axis will be like this, 1 over n, 2 over n, etc. Up and down jumps to be equal and size 1 over square root n. Okay, so I think we can draw it like this here. So this is time, 1 over n, 2 over n, 3 over n, 4 over n. Okay, so it starts at 0. Here it is. So this is your BNT. Okay, so BN0 is 0, 0. it says that it may go up or down, and the size of the jump will be 1 over square root n. So let's say it go up to here. So this will be 1 over square root n. If it goes down, it will be minus 1 over square root. Okay. So let's say we are here now. The process may go up or down. Either we go up or down. Up to 2 over square root n. Or 0 itself. And here, I'm changing colors just to be for you to be able to understand the illustration. This one go up, minus 1 over square root n plus 1 over square root n becomes 0. And maybe going down once again. So this is minus 2 over square root n. So it goes on like this, huh? We go up once again to 3 over square root n, down, this up, down, etc. Okay. So it says something here. The probability of going up or down is half. So it is equiprobable of going up or down. Thus, if xi is a sequence of independent binomial random variable, taking the values plus 1 or minus 1 with equal probability, then the value of Bn at the ith time step of length 1 over n is Bni over n plus Bni minus 1 over n plus xi over square root n. Okay, so to be more precise here, I will say that this is Bernoulli. Okay, so your xi may be either plus 1 or minus 1. Plus 1 with probability half, plus 1 with probability half. This is what is said here. Okay, so what is being written here is that, let's say, here is I over n. And let's say we are here. We stand here. N minus 1, I minus 1 over n. So we are speaking of this. So this is Bn I minus 1 over n. Okay. Let me write it clearer here. N I minus 1 over n. Good. So for the next time step now, let's say here. So here is I over n. So what happens? Either this go up to Bn I minus 1 over n plus 1 over square root n, or it goes down to Bn I minus 1 over n minus 1 over square root n. So what we have done is that we replace, you will see that here it is. So we replace the xi by a random variable, which is Bernoulli, taking value plus 1 or minus 1. Okay. So here it is. This is our random walk. And I think you will recall that we have done this previously in the module stochastic processes, where we have seen, for example, that we have, I think it was written like this, mu plus xn minus 1. Okay, plus Zn, where your Zn may take value plus 1 or minus 1. This is with probability half. I've seen this last year in the module stochastic processes. Okay, so it was in tutorial 1, I think, tutorial 2. Good, when we spoke about stationary processes. Good. So the time steps may be decreased towards 0. So this is our aim here is to make that random walk converge to a continuous time model. We know that the random walk is defined as a discrete time model, so we want this to converge towards a continuous process. So how do we do that? In let's say, for example, in an interval of 1 unit of time, let's say I have time steps here. I want this n time steps to increase towards infinity. What happens is that I will have an infinity of time steps in that interval 0 to 1. Okay, so finally it is converging towards a continuous process. So we are increasing the sampling rate in that, in fact, we will be having more Bernoulli random variables within that same time interval 0 to 1, for example. So consider the distribution of Bn now at time 1. So let's say we reach here n over n. So it is time 1. Let's go to 1. So I will be having, let me take the highlighter. So at this time 1, I will be having many points here, because when I will continue my process here, this process will give many different final values for my process. For example, I will be having a price here. So the first price, what will be the highest price here? So it will be n times. So because I have n time steps, time the magnitude of the ump jumps. So the n times that I'm calculating the different time steps, I'm having only up jumps. So it will be n over square root n. So it's equal to square root n. So the lowest one will be, so n time steps times only down jumps. So this is equal to minus square root n. This will be 0. So we will be having other values like this, going like this. Okay. So by induction, there are n plus 1 possible values it can take. Okay. How can we say that? In that here we have 0, we are at the time instant 0. How many nodes do we have? 1. Here we are at the first time step. How many nodes do we have? 2. Second time step, we have 3. Third time step, we have 4. N over nth, the time step which relate to n over n. So it is the nth time step. So it will have n plus 1 nodes. So these will range from, and this is what we just have just written on the plot, range from minus square root n up to square root n. Good. So these are MATLAB simulations. Okay. So I do have the codes. I may send them to you on Google Classroom. So for example, here I'm taking only one trajectory. So let's say m is the number of trajectory and n is the number of time steps that I'm including from 0 to 1. Here it is n squared to 10. So then on MATLAB, I simulate a trajectory for my random walk. So it has gone down, down, up, down, 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 up, down, down, down. Okay, this is one trajectory. Good. And here what I've done, it is still one simulation, but with 100 time steps. So down, 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 up, up, down, up, down, 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 up, 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 down, up, down, etc. I think you understood. So what we want to do is to make n tend to infinity. Example here, we have m squared to 1, so we have only one trajectory, but n squared to 1,000 simulation. So we start saying the evolution of the random walk being quasi close to continuous. Okay. And here we still keep n squared to 1,000, but we are taking 10 trajectory. Okay. So 10 simulations. Good. So what we want to do is to use the law of large numbers to be able to deduce the distribution which is happening here for Bn1. This is our idea here. We want to have the distribution here. So for this one, then it won't suffice. We want to take more. So here m is equal to 100, n is equal to 1000. But we take 100 simulations. So we do see the 100 simulations, how the random walk is evolving. Here we take 1,000 time step, but we are taking 1,000 simulations. So here we can try to deduce what is happening here. So I would like to show you something is that we want to understand, to deduce the distribution of these values which appear here at 1. We want these values, the distribution of these values. But just to be able to give a hint, let us try to see what is the range of these values here. You see it is from -3 to 3. -3 to 3. Good. So this is just a hint. We will see later on what happens. So here it is. You understand that Bn1, these are values of Bn1. Okay. For example, for this one, it is Bn, it is Bn2 over n, where n is equal to 10 is here. Okay. For example, say no for this one here, it is Bn2 over n also, but here n is 100, it's equal to 100. Okay. So what I want is Bn of 1. What is Bn of 1? It is Bn n over n. So we are speaking of these points which appear here. So at the, we want the distribution of this. So how do we do that? Let's just try to calculate the expectation, the variance, and trying to deduce what is the mean, what is the variance, and what is the distribution afterwards. Okay. So Bn of 1 is equal to Bn of n over n, and we are given the formula of this. So let us use this. Becomes B of n minus 1 over n plus xn over square root n. Use this. Okay. So this will be Bn minus 2 over n plus xn over square root n plus xn minus 1 over square root n. I'm still using the same formula. So let me write this in terms of n minus 3 now. Bn n minus 3 over n plus xn over square root n plus xn minus 1 over square root n, xn minus 2 over square root n. So we go on like this until we have Bn of 0 over n. So what is Bn of 0 over n? It is the point which is here. And we know it is 0. This will be 0. And it will be still plus something. Okay. And we know that will be by induction I is equal to 1 up to n of xi divided by square root n. So now we can apply expectation. So expectation of Bn1 will be the expectation of this. This is 0. We can put the square root n outside. So put the sum outside because it is the xi are Bernoulli independently distributed. Okay, and they are all identically distributed following a Bernoulli distribution of 1 minus 1. Okay, 1 minus 1. So it will be expectation of xi over square root n. So let's find the expectation of xi. So let's put it x itself because identically distributed may following the same x here. So independent of the I. Okay. So we know that it will be p up, if you want, p up times the value of the up. It is, sorry, yeah, times the value of when it goes up plus 1 plus p down times the value of when it goes down. So it is half times 1 plus half times minus 1. It is 0. So this summation is 0. Good. Let's now try to do the calculation of variance of bn1. So it becomes variance of summation I equal to 1 up to n of xi divided by square root n. So what we do, we remove the constant outside, becomes 1 over n on square root n raised to the power of 2. And we also put the summation outside. Why? Because the xi are independent to each other. Xi independent to xj for I not equal to j. Okay, so we can write it like this. Otherwise, there would have been covariance terms. Okay, so to n. So what is variance of x? Variance of x will be equal to expectation of x squared minus expectation of x to the squared. So this is 0, and we calculated it here. So what is expectation of x squared? So let's take values of x. So for example, let's take pu times the value of up to the squared plus p down plus the value times the value of down to the squared. Okay, so it becomes half times 1 plus half times 1 becomes 1. So here is 1. So summation of 1 from I squared to 1 to n becomes n over n. So this is 1. So we see that the bn1, okay, it has 0 as mean and 1 as variance. Okay, so just to give a hint, once again, minus 3 to 3. So for minus 3 to 3, for which variable random variable do we have a spread around minus 3 to 3? And here we know that it is following a distribution with mean 0 and variance 1. Okay, so here is the answer. What happens as n becomes very large, that is the time steps become very small, by the CLT, the central limit theorem, these binomial distributions tend towards the unit normal distribution. The unit normal distribution. N01. So Bn1 follows N01. What happens to Bnt? So what happens is that we had this 0 up to 1, and we said that here we have n time steps. Now what happens is that we have t like this, and we have n time steps in all these. So we have t units of 1, where each one interval, unit interval in the time has n time instants. So in total here we have nt time steps. Okay, so after this simplification, we can write this bnt1 times square root t. Good. So what is bnt of 1 when n tends to infinity? I know that bn of 1 tends to asymptotically to n01. Now I say that I have n time steps, and I make that n tends to infinity, I get that distribution here. And if I put n times t, t is positive. Good, t is positive. And n is tending to infinity. So I still have the n01. So your bnt, which is here, which is equal to bnt1 times square root t. So here it is. I know that this will follow an n01 when n tends to infinity. Okay, times square root t. So your square root t, when it goes inside, it will become n0t. So your variance, because when it goes inside, it is the variance which is related to the second parameter. So square root t becomes square root t to the square. Okay. So your bnt follow a normal 0t. So I think this is giving a hint on what will be the distribution of the Brownian motion. Okay. So in the limit of infinitesimal time steps, so infinitesimal means very small, very, very small. In the limit of infinitesimal time steps, the discrete time binomial can be modeled by the appropriate normal distribution. Okay. Each random variable BNT has the property that its future movements away from a particular position are independent of where that position is. At its history up to that point. So any future displacement bnt plus s minus bns is binomially distributed with zero mean and variance t. As the sampling rate increases, the distribution tends to n0t. Good. So what does this mean? Is that okay? Actually, we started here and we said that this is 0 and this is t. Good. So since we are working with a random walk, we understand that, let's say I give you the value here. You don't need to know whether it has gone down, up to reaching here, or whether it has gone only up and then down to here. You don't need to know these. If you have this point, you know that it will go either up here or down here. You don't need to have the history up to here. So it has the independent increment property. Okay. So this is what has been said here. Its future movement away from a particular position or independent of where that position is, it is slowly up to that point. Okay. So now what happens is that say that this is S, this is T plus S, T plus S. So we have a time interval of T. Okay. And I'm saying to you that we are at BNS here. Okay. And I don't know what will be BNT plus S because I'm standing here. It is saying that because we are working over T, T unit of time, okay, your BNT plus S minus BNS will be having the same distribution as BNT, hence a normal 0T. When n, small n tends to infinity, the sampling rate tends to infinity. This is what is being said here. Okay, so having done this, okay, so you won't be examined on this part, on the construction towards the Brownian motion. Okay, so this is only for better understanding the Brownian motion. Okay, so this leads us to define specifically the Brownian motion. So we will start by defining the standard Brownian motion, which is also known as the Wiener process. So the stochastic process B is a Brownian motion or Wiener process. Okay, Wiener is Wiener. If and only if BT has independent increments. So I think you're already aware what is meant by independent increments. So it is defined here, the increment bt minus bs. So it is defined over the time interval s to t. So bt minus bs is independent of the history of what has been happening up to the time s. So the process is defined here. So it is independent to the everything what has happened that has happened before the time s. So here it is written mathematically bt minus bs independent to fs. What is fs? It is the history of information up to time s. So it is well summarized here. bt minus bs independent to the stock of information up to time s. This is the first feature of the Brown motion. Secondly, bt has stationary increments. That is, the distribution bt of bt minus bs depends only on the time increment t minus s. Thirdly, bt has Gaussian increments. So bt minus bs follow a normal 0 t minus s as parameters. bt minus bs follow a normal 0 t minus s. So this is very important. This is very important. Fifth, b0 is equal to 0. So that process starts at 0, at time 0. The term BM, Brown motion, can also refer to a process WT. So the Brown motion may be also a process WT which satisfies the first, second, and fourth condition. So the first, second, and fourth condition with the following distribution. So WT minus WS following a normal mu into T minus S, second parameter being sigma squared T minus S. Okay, so we will see a particular Brown motion afterwards, which is known as the geometry Brown motion. Okay, so, and this is very crucial, very essential for the modeling of stock price. The relationship between the standard Brown motion and the Brown motion is the same as that between n01 and n of mu t man and sigma squared t. So I think this is quite straightforward. It is as if I'm saying that y following a normal 0, 1, and then I'm saying that x is equal to a plus by. So what will be the distribution of x? It will be a plus, as if 0 of b squared, so following a normal a plus b squared. I think you already know this. Good. So this is a property of the Brown motion, Wiener process. Covariance of BS-BT is equal to the minimum between S and T. So this is only a notation. Huh? So minimum between N, S and T. So I think while we are doing all this, it is you are being reminded about the Poisson process that we have seen in stochastic process. Why? Because the Poisson because the Poisson process is a process which also possesses the independent increment property and the stationary increment property. But here it followed a Poisson distribution. So in our case, the Brown motion is also independent and stationary, but the distribution is a normal distribution here. So let us see how do we do this, the covariance of BS and BT. So I will try to put forward the increment properties as we have done here in this chapter process previously. What you have done, we try to put forward the increment properties so that we are able to use them. So here, for example, so let's say S is less than T. So we are taking the first case. So it will become BS. Let me write this. BT minus BS plus BS. The same thing here. So what we do, BS, BT minus BS plus covariance of BS, BS. BT minus BS. So what is the covariance of BS and BT minus BS? It is the covariance between BS and BT minus BS. It will be 0 because due to increment property, we have that the BS is independent to BT minus BS. Plus, what is the covariance of BS? BS. It is the variance of BS then. It is the variance of BS. So we know that BS follow a normal 0 S. Okay. So the variance of BS is equal to S. So when S is less, so this is the first case. When S is less than T, the result is S. So if we take the second case, S strictly greater than T, when you go down with the calculation, you will see that the result is T. So what happens is that covariance BSBT is equal to the minimum between S and T. And the answer is here. So let us give some properties of the Brown motion. So firstly, we've just seen this, the covariance between BT and BS is equal to the minimum between T and S. Secondly, BT is a Markov process. So what is meant by Markov process? It has the Markovian property in that the inference on the future depends only on the present and not on the past. So this is true. This Markovian property is a result of the property due to the independent increments. Thirdly, BT is a martingale. So this is important. We'll see these more specifically in the coming weeks. So what is a martingale? It is defined like this. The expectation of BT given Fs is equal to Bs. So what is being said here? So we are standing given Fs, and so we are standing at S. So this is BT, which we don't know. So we are standing at S. So we know the stock of information, Fs. We know all these informations up to S. And the process, the Brown motion process, has a value Bs here. It is saying that taking the expectation on BT, which is in the future, given the stock of information at S, will give as result B of S. This is the definition of a martingale process. So in the coming weeks, you should be able to do the calculation to check whether a process is martingale or not. We will see that later on. Okay. So Brown motion, we are working with a Brown motion in only the one dimension. So Brown motion may be defined in 2 dimensions, etc. So you may read this property which relate to this to show 2-dimensional, etc. Feature 5, the standard Brown motion has a scaling property. It says that when I define a process like this, where BT, so your BCT is given like this, BT is a Brown motion here, we can say that this specification here, B1T, is also a Brown motion. We can check this. Okay. So what you can do to check this, you can go back to the definition here. So because it is saying if and only if. So if you have a Brown motion, you're sure you will be having the one process, you will be having these 5 conditions being satisfied. Okay, so if you have a Brown motion, if Brown motion, then you have 5 properties being held. And if and only if also says that if I have a process which have the 5 properties, this means that then we have a Brownian motion. So it goes the two way, in the 2 directions. So you can check this using these 5 properties, but we will see in the next slide that we have another definition for the Brown motion, which we also can use. So we also have the inversion property of the Brown motion, which is defined like this. So Bt is a Brown motion. Bt is a Brown motion. So B2T, which is defined as T times B with the subscript being 1 over T, is also standard Brown motion. So we can check these using these 5 definitions of the Brown motion. Good. So although BE is continuous everywhere, it is with probability 1 nowhere differentiable, that is the values of W are zigzag. So for a Brown motion, a true one, so a continuous time process, let's say it is like this. When we see the process, it is like this. What is being said here is that if you take the zoom and you zoom here, you magnify this part, what you will see? You will see another process like this. And then you zoom here, you will see another process like this. So what happens is that the process is always exact. There is no smooth evolution of the Brown motion. That's why it is nowhere differentiable. Okay. So by implication, the limit as time become continuous, dbt follow a normal 0 dt. Okay. So bt follow a normal 0 t and dbt follow a normal 0 dt. Good. So I define a martingale here. Process S is a martingale with respect to a measure P. Okay. Probability measure P. Because we will see later on that when we work with option pricing on a given stock, we can do the pricing, the fair pricing, only using the risk neutral probability measure. So we will see that there is a market probability, historical probability if you want, and we have also a risk neutral probability. So that's why you will see that in the definition we give that specification on the which probability we are working. Okay, so it is a martingale with respect to a probability measure P and a filtration Fi. So you understand that what is Fi? So this is 0, this is I, this is J. So Fi will comprise all information on the stock up to the time I. Okay. So the expectation of Sj, so Sj is here, this is Si. The expectation of Sj, which is unknown, given all the information which is here, will give us Si. This is the definition of a martingale. So I think in the tutorial 1, you are asked to check whether processors are martingales or not. Good. So this is another definition for the Brown motion. A real valued process Bt is a Brown motion starting from 0 if and only if. So here also it works in the both directions. So if we have these properties being held, have a Brown motion. If we have a Brown motion, we will be having these properties which are holding. So first property, we have that it is Gaussian. So if you have, let's say, if I go back, let's say I'm giving you this definition. I'm asking you to check whether this is Brown motion. You do? You first check whether it is Gaussian. Second, you take expectation on that B1T here. Check whether the expectation is 0. Check whether BSBT has an expectation which is equal to the minimum between S and T. Okay, so I think you will agree that covariance BSBT is equal to the expectation of BSBT minus the individual expectation. And this is equal to 0. This is equal to 0. So in fact, we are checking the covariance when we are doing this calculation. But to go more quicker, we can check only this part because this is 0. Expectation of BSBT should be equal to the minimum between N and ST. And lastly, BT is a function continuous in time almost surely. So it is continuous in time. Good. So you can do this exercise. So let me do it here. So expectation of BT given Fs. So what I want to do, once again, I want to put forward my increment properties. So I write it like this, as always, given Fs. So it is expectation BT minus Bs given Fs plus expectation Bs given Fs. Now, this, we are at S. We know all the information up to and including S. So Bs is no more stochastic, it is deterministic here. You can put it outside, it becomes Bs itself. And this part, Bs minus Bt given Fs. So we know that by the independent increment property, we have Bt minus Bs being independent to Fs. So I can remove the conditional here. And what is the expectation of this? This is 0, because it follows a normal Bt, a normal 0 T minus S. So this is your answer. And it is Welle martingale. Why? Because expectation on Sj given Fi is equal to Si. So it is same here. Expectation of Bt, T which is greater than S given Fs is equal to Bs. So I do have the martingale property. Second, you can prove the scaling property and time inversion property of the Brown version. So I'm advising to use this set of properties to check whether B1T and B2T are Brown motions. Okay, so you can check this. I think I already uploaded the proof for the scaling property on Google Classroom. Good. So this is just a summary of the different properties that we have seen for the Brown motion. So representation of asset prices. So we will be using the Brown motion here. So the previous properties have important consequences for the use of Brown motion as a model for stock prices. We suppose that the stock was deterministic with share price ST at time t. Then in infinitesimal time step dt, the stock price jumps and would obey the equation dst is equal to mu dt. So we have seen this previously. When we do the integration both parts, we will have this. You will recall that previously we've got this. mt is equal to m naught exponential rt. Okay, so this is purely deterministic. It has no random component. So this is not appropriate, adequate for practical market modeling. So we consider the geometric Brown motion. It is given by this. So this is the expression for the GBM. This is a very important process, the geometric Brown motion, and this will be used for pricing options using the Blaschko's formula. So DST over ST is equal to mu dt plus sigma dB, where dB follow a normal dt. So B is a Brown motion here. So now what happens is that we understand that S is not deterministic. You can't say, give me a forecast for S. So I want a single value for S. So this is not okay. Why? Because we do have a random variable here. Okay, dbt is a random variable. So you won't be having only one value. However, you can have a distribution of that stock price SC. Okay, and any statistical feature which come along with the distribution. Okay, so we will see later on when we will do, for example, the Ito Zema to show how do we have simplify from this to this to show that finally that ST follows a log normal distribution, and this is in line with assumptions which are usually made in market analysis, in financial analysis. We assume that the log returns follow a normal distribution, and this is what we see here. So ST follow a log normal, and the log of ST, okay, follow a normal distribution. So when I'm speaking of log, it is natural log, ln. Good. So when I have this, I can simplify to have that ST is equal to SU exponential of mu minus sigma squared over 2 t minus u plus sigma into square root of t minus u times x, where x follow n01. So I want you to well understand, so this part we will do afterwards. But from here, going down up to having this, I want you to try to understand how do we have this. So this is very simple, very, very simple. But I want you to go through. So the above model is not used to predict ST. So we don't use this model to do only to do prediction for ST. I said previously, since it has a stochastic part in it, a stochastic variable in its definition, I can't give only one value. Okay, so it may be giving the worst case scenario or best case scenario, etc. So it is more used as a tool for simulating security prices. So I can simulate not only one price, but I can simulate like 1,000, 10,000, or 100,000 possibilities for the price of ST. Okay, so using this distribution, I'm able, for example, to calculate probabilities, expectation, variance, value at risk. So it is quite some very important properties of my distribution, which may be calculated using this information here. So how to fit the model to the experimental data for a particular stock? We can use market data to calculate mu. What is mu? Mu is that drift. So we calculate the returns. So using market data, so returns are given by this log of Sj plus 1 divided by Sj. Okay. So we sum the returns and we divide by n times dt. Sigma squared, which is the volatility, will be in fact the standard deviations of the log returns. So you will see here, these are Ij minus mu dt, which is its corresponding mean, okay, raised to the power of 2. So it is a deviation raised to the power of 2, summed and divided by the number of data. So it is a standard deviation itself of the log return. Good. So you won't be necessarily required to do so unless it is done in an assignment, etc. So expected value and variance of log normal prices. So you are given the calculation for the expectation. I want you to go through and understand, and then be able to do the calculation for the variance of ST given SU. So your ST here, you will be using this. Okay. So everything in this formula are deterministic except this. So your ST is given by deterministic by a set of deterministic parameters plus one stochastic part, which is this X here, which you will replace here to be able to do the calculation. Good. So we will end here because in the next lecture video, we start by explaining how do we calculate the probability of a fall in share price.